Here's a thought that keeps me up at night. Right now, as you're watching this, there might be a civilization out there, smart, curious, maybe even desperate to find us, and they have been traveling toward us for longer than human civilization has existed, and they're still not even close. Not because their ships are slow, but because space is not what you think it is. Space is not empty distance. Space is time, incomprehensible, crushing, merciless time, and once you understand that, really understand it, you'll never watch a science fiction movie the same way again. Because the problem with alien visitors isn't technology, it's arithmetic. Let me start with something simple. Something so simple it almost feels stupid. But it isn't stupid. It's the most important thing I can tell you today. Space is big. I know. You've heard that before. But I don't think you've actually felt it. Not really. When people say space is big, they usually mean it in a vague, hand-wavy kind of way. Like saying the ocean is wet. Sure, technically true. But it doesn't capture what's actually happening. So let me try to make you feel it. The sun is about 93 million miles away from Earth. That's already a number that most human brains can't really process. But let's try anyway. If you could drive a car at highway speed, let's say 60 miles per hour to the sun, it would take you about 177 years. Not days, not months, years. And you'd need to pack a lot of snacks. Now, light is fast. Light travels at about 186,000 miles per second. That's so fast that light can circle the entire Earth 7 times in just 1 second. So light gets from Earth to the sun in about 8 minutes. 8 minutes, that's genuinely fast. But here's where things start to fall apart. The nearest star to our sun is called Proxima Centauri. It's our closest neighbor in the entire universe. And how far away is it? About 4.24 light years. That means light, the fastest thing in the universe, takes 4.24 years to get there. Not hours, not days, years. Now, let's think about what that means for a spacecraft. The fastest spacecraft humanity has ever built is called the Parker Solar Probe. At its peak speed, it travels at about 430,000 miles per hour. That sounds incredible. And honestly, it is incredible. It's an engineering masterpiece. But if we pointed that spacecraft at Proxima Centauri today, it would take about 6,300 years to arrive. 6,300 years. When the pyramids of Egypt were being built, that spacecraft would be just getting started on its journey, and it still wouldn't be there today. It wouldn't even be halfway. Now, I want you to sit with that number for a second. Because most people hear it and think, okay, but what if we build a faster ship? What if we use some new propulsion system? What if we figure out nuclear fusion drives or ion engines or some technology we haven't invented yet? Fair question. Let's play that game. Let's say somehow we build a ship that travels at 10% of the speed of light. That would be extraordinary. No one has ever done anything close to that. But let's say we do it. At 10% the speed of light, it would take about 42 years to reach Proxima Centauri. That's still a human lifetime. You'd have to be born on the ship, live your whole life in a metal tube floating through nothing, and maybe see the destination before you died. But let's go further. Let's say we get to 50% the speed of light. Half the speed of light is almost unimaginably fast. The amount of energy required to accelerate even a small spacecraft to that speed is beyond anything we currently know how to produce. But let's say we do it anyway. At half the speed of light, the trip to Proxima Centauri takes about 8.5 years. That's manageable for a human crew. So maybe this is where hope lives. Except here's the problem. Proxima Centauri is the nearest star. It's the closest one. And even if there were a civilization there, which we have no evidence of, getting a signal back from them would take another 4 years at the speed of light. So we're already talking about a round-trip communication time of over 8 years just to the nearest star. But the real universe isn't just Proxima Centauri. The real universe is vast beyond anything our minds were built to handle. Our galaxy, the Milky Way, is about 100,000 light-years across. That means even light takes 100,000 years to cross it. A civilization on the other side of the galaxy, traveling at 10% the speed of light, would need over 1 million years to reach us. 1 million years. Let me put that in perspective. Homo sapiens, modern humans, have only been around for about 300,000 years. 1 million years ago, our ancestors were not even fully human yet. They were using rough stone tools and living in small groups. So a journey that takes 1 million years isn't just long. It's longer than our entire species has existed, multiple times over. And that's just our galaxy. The observable universe contains about 2 trillion galaxies. 2 trillion. And the nearest large galaxy to ours, the Andromeda Galaxy, is about 2.5 million light years away. So if you wanted to travel to the nearest galaxy at the speed of light, it would take 2.5 million years. At any realistic spacecraft speed, we're talking tens or hundreds of millions of years just to reach the next galaxy over. Now here's the part that I find most fascinating. People often ask, well, maybe aliens have technology we can't imagine. Maybe they've solved the energy problem. Maybe they have warp drives or wormholes, or some exotic shortcut we haven't figured out yet. And look, I understand why people say this. It feels like a reasonable objection. We can't know what future technology looks like. But here's where physics gets completely ruthless. The speed of light is not just an engineering limitation. It's not like the sound barrier, which people once thought was impossible to break and turned out to be quite breakable. The speed of light is a fundamental property of the universe itself. It is woven into the fabric of space and time. Einstein showed us this over 100 years ago, and every single experiment we've done since, thousands of them, has confirmed it without a single exception. Nothing with mass can travel at or beyond the speed of light, not because we haven't tried hard enough, but because the physics literally doesn't allow it. As you accelerate toward the speed of light, something remarkable and terrible happens. You need more and more energy to keep going, and not just a little more. The amount of energy you need grows toward infinity as you approach light speed. That means to actually reach the speed of light, you would need infinite energy. And there isn't infinite energy available in the universe. The universe has a lot of energy, but not infinite. So the speed of light is not a goal we're trying to reach. It's a wall we can never touch. Now, some people bring up theoretical ideas like wormholes or warp drives. And yes, in the mathematics of general relativity, these things appear as possible solutions. They're real solutions to Einstein's equations in certain mathematical contexts. But there are enormous problems with turning them into physical reality. Wormholes, if they exist at all, would likely be microscopic, smaller than an atom, and they would instantly collapse under their own weight before anything could pass through. The exotic matter needed to hold a wormhole open appears to violate basic physics principles that we've never seen violated in any experiment. Warp drives, in theory, require negative energy, a form of energy with properties that seem to break the rules of physics as we understand them. Some physicists have proposed creative workarounds, but none of them hold up under close examination. They all run into walls of their own. These ideas are not secret technologies that advanced civilizations have already figured out and are keeping to themselves. They are theoretical puzzles that may not have any physical solution at all. We don't know for certain, but we have very good reasons, backed by a century of tested science, to be deeply skeptical. And even if some exotic shortcut existed, even if there was some workaround buried in the mathematics, the energy requirements would still be almost impossible to imagine. We're talking about amounts of energy that might require harnessing the total output of a star for one trip, one way. Think about what that means for any alien civilization. Even if they were thousands of years more advanced than us, even if they had solved every engineering problem we can think of, sending a spacecraft to another star system would be the most expensive project they could ever attempt. It would drain resources on a planetary or stellar scale, and they would be doing all of this to visit a star they probably don't even know has intelligent life on it. Because here's something else people forget. We haven't been announcing our presence for very long. Radio waves travel at the speed of light. Our oldest radio signals have only traveled about 120 light years into space. The Milky Way is 100,000 light years across. That means our signals have only reached a tiny fraction of our own galaxy. Most of the stars in the Milky Way have never received any evidence that humans exist at all. So an alien civilization, even one that is actively looking for neighbors, would have no reason to come here. We're not on any interstellar map. We're not sending up a flare visible across the galaxy. We are a quiet little planet around a quiet little star in a quiet corner of the Milky Way, and we've only been making any noise at all for about 100 years. Now, some people say maybe aliens have giant telescopes, and they can see our atmosphere and detect signs of life. And yes, that is possible. We're starting to do exactly that ourselves with telescopes like the James Webb Space Telescope. We can look at distant planets and analyze their light for chemical signatures that might suggest biology. But again, distance matters brutally here. If an alien civilization 1,000 light years away, detected signs of life on Earth today, they'd be seeing light that left Earth 1,000 years ago. They'd be looking at Earth during the Middle Ages. Then if they decided to send a ship, it would take, at the very best realistic speeds, thousands or tens of thousands more years to arrive. By the time they got here, human civilization might not even look recognizable. We might be something completely different. Or we might be gone. This is the time problem. And it's just as devastating as the distance problem. In fact, they are the same problem. Because in space, distance and time are inseparable. When you look at a star 100 light years away, you are not seeing it as it is now. You are seeing it as it was 100 years ago. The universe doesn't show us the present. It shows us the past. Always the past. This reframes the whole question about alien contact. People frame it as a technology question. Why haven't they built a good enough ship yet? But the real question is a time question. And when you ask it as a time question, the fog clears up fast. Even a civilization 10,000 years more advanced than us, which would be a lid so enormous we can barely picture it, is still constrained by the same physics. They still can't travel faster than light. They still face the same brutal distances. And they still have to reckon with whether a journey measured in millions of years is worth taking. Let me make this even more concrete. Imagine you are an alien scientist on a planet 50,000 light years from Earth. You've detected some faint radio signals from our direction. You've figured out there might be something interesting over here. What do? You could build a ship, you could send it, but because your physics is the same as ours, that it will take millions of years to arrive even at extraordinary speeds, your entire civilization will have risen and fallen many times over before the ship gets anywhere near Earth. You know that you personally will be long dead, and you know that whatever is at the destination when the ship finally arrives might be completely different from what you detected when you launched. Do you still do it? Maybe, if you are driven by pure curiosity and have unlimited resources, but it is nothing like hopping in a car to visit someone across town. It is a commitment that spans geological timescales. Now, I want to talk about energy one more time because I think people seriously underestimate just how bad this problem is. To accelerate a spacecraft with a mass of about 1,000 tons to just 10% of the speed of light, the energy required is roughly equivalent to the total energy output of the sun over several full days. The entire sun, multiple days of output, just to get one ship to a fraction of light speed. And here is the part people always miss. You need just as much energy to slow down, because if you are traveling at 10% the speed of light and you don't decelerate, you smash into your destination at a speed that turns the ship and everything in it into a brief flash of hot gas, so the energy cost is at minimum doubled. You pay once to speed up and again to slow down. And we haven't even talked about the rocket equation problem. The more fuel you carry, the heavier the ship gets. The heavier the ship, the more fuel you need to move it. The more fuel you add, the heavier it gets. Again, it's a vicious cycle, a tyrannical loop. Rocket scientists have known about this for over 100 years, and it doesn't get less brutal with time. It just sits there, patient as gravity, demanding its toll. Some people propose beautiful solutions to this: solar sails that use the gentle pressure of starlight, laser arrays that push a light sail from behind, fusion drives that extract enormous energy from hydrogen, antimatter engines that convert mass directly to energy at nearly perfect efficiency. These are fascinating ideas. Some of them might actually work for tiny probes, maybe something the size of a postage stamp. But scaling them up to carry living beings across interstellar distances is a completely different challenge. Because we're not talking about launching a small probe. We're talking about a ship that can sustain living creatures for potentially thousands of years. A ship that carries food, water, air, medicine, ways to handle psychological stress, social structures, and some means of keeping beings sane while they float through empty space for generation after generation. This is the generation ship problem. Even if you solve the energy problem completely, you'd face the biology problem. Can humans survive psychologically for thousands of years, locked in a metal container with the same small group of people? We don't know. The psychological effects would likely be severe. Cosmic radiation at those velocities could be damaging to biology in ways we haven't fully studied. The social effects of extreme isolation, stretched across multiple generations, are almost impossible to predict. And all of this applies equally to any alien species trying to visit us. They have biology too. They have limits. Physics doesn't make exceptions for civilizations that are older or smarter. Now, here's something I think about a lot, and it connects to a famous puzzle called the Fermi paradox. Enrico Fermi, a brilliant physicist, once sat down at lunch and asked a simple question. If there are so many stars, and if life can arise around many of them, and if some of those civilizations are millions of years older than us, why haven't we seen any sign of them? Why is the universe so quiet? The answer I'm giving you today is not the only answer people have proposed, but it's one of the most important pieces. The universe is quiet, not because no one is out there. It may be quiet because the distances are so crushing that even radio signals take thousands of years to arrive, and physical spacecraft would take millions. The universe doesn't allow fast connections. It enforces a kind of cosmic quarantine on every civilization, whether they like it or not. And I find something quietly beautiful in that, even though it sounds lonely, because it tells us that the universe is not a network of easily connected civilizations swapping information and visiting each other. It is a collection of isolated islands, each separated by oceans of time so wide that crossing them might be effectively impossible in any practical sense. Each civilization gets to know the universe from its own little corner, with its own instruments, through its own patient observations, and it might send out signals into the dark, not knowing if anyone will ever receive them, not knowing if any answer will come back in its lifetime, or in any lifetime. We do this right now. We point our radio dishes at the sky and listen. We send out messages. We study the light from distant stars for signs of technology or chemistry that suggests life. We do all of this knowing the answer might not come for thousands of years if it comes at all. And I think there is something deeply honest about that, something that reflects what science actually is at its core. Science is not about finding quick answers. It's about asking good questions and being patient enough to wait for the universe to answer in its own time. The universe moves slowly. It doesn't care about our schedules. It doesn't care that we're curious and impatient and full of hope. It runs on physics, and physics runs at exactly the speeds it runs at, regardless of what we want. The aliens aren't coming, not because they don't exist, not because they aren't curious, but because the mathematics of distance and the physics of speed have built walls between every civilization in the cosmos. Walls made of time, walls that even the most advanced technology we can honestly imagine would struggle to breach. And understanding that, really sitting with it and letting it sink in, changes the way you look at the night sky. Those stars aren't just pretty lights. They're places, real places, with real distances, separated by real spans of time, so vast that they make human history look like a heartbeat. Every star you see is a reminder that the universe is not built to be easy. It's built to be understood, and we are understanding it. Slowly, carefully, one equation at a time. That's what physics is for. Not to make the impossible possible, but to tell us clearly, honestly, and without flinching, exactly what is possible and what is not. The stars are far, the distances are real, the time required is millions of years, and that is not a failure of imagination. That is the universe telling us the truth. I'd rather have the truth than a comfortable story any day.